So here's some food for thought. Everything is analog. The camera I'm filming this with is analog. The computer I edited this video with is analog. And even the computer or smartphone you're watching this on is analog. The reason I'm saying this is, well, because of a discussion on the internet. Where else? This discussion was about a little synthesizer, a noise box. Somebody made a synthesizer using logic chips and makes a wonderful record. But since they used logic chip, people are arguing that it wasn't an analog noisemaker but a digital one. The analog versus digital discussion is as heated as ever, especially among synthesizer fanatics. So here's my little take on it. Every circuit by default is analog. It's rather the definition or function we give to a circuit that makes it digital, not the circuit itself. So I'm gonna sketch out two scenarios that illustrate this. So, well, let's head over to my desk and let's get drawing. So usually when people think about analog signals, they think of the sine wave. Here's a beautiful sine wave. So let's put a sine wave between 0 and 5 volts, which is kind of the voltage range of 5 volt TTL logic. Now, to illustrate the first concept, I'm going to take an amplifier first. So here we just have a simple amplifier. And we're gonna give our amplifier a range between ground, which is 0 volt, and, well, you guessed it, 5 volt. And we're gonna set the gain way up high. Now what happens is, essentially, it will turn our sine wave into what people think about when they think about digital electronics, digital circuits, the square wave. Now let's take a digital chip. Let's take an inverter. The 4000 series inverter. There are quite a few of those. Let's put our sine wave in there. Well, what happens? Well, again, we get a square wave, except this time it's inverted. Now, normally at unity gain, so the gain would be 1, then whatever comes into the amplifier also comes out, just the same, unchanged. When we look at our graph of the transfer, we'll get a straight line. And this line, for those who are not in the know, illustrates the relationship between input and output. Now, when I raise the gain, this line will become increasingly skewed because our amplifier is limited between 0 and 5 volt. Now I increase the gain, it will start getting skewed. And our sine wave will get a bit more square wavy. Now in the case of our logic inverter, this gain is so high that you essentially get this. So you have so much gain, every transition period, which is this area here, kind of just switches between the minimum and maximum voltage. So we get our square wave. You could argue that this logic chip, this digital chip, is nothing more but an amplifier with a lot of gain. Now, to illustrate the final idea and the difference between digital and analog, I'm just gonna quickly draw. Not very good at drawing through the camera like this, but oh well. So again, everything is powered from a 5 volt single rail supply. Now here's our circuit. We have a 40106 square wave oscillator, and we have a 4000 series TTL logic binary counter. Now you can look at this circuit in two ways. The first way you can look at it is this over here. This is a square wave oscillator. And it generates an analog square wave. Then the binary counter divides this down into octaves of square waves. Essentially what happens in a binary counter, for those who don't know, it counts in binary from 0 to 255. This means if we look at this in the analog way, we essentially just see 8 octaves of square waves. Of course, the 8th is the lowest octave and the 1st is the highest octave. So essentially what we have here is an analog square wave oscillator and an analog frequency divider. Now let's look at this the digital way. It's the exact same circuit, we don't change anything, but this will be the clock. It generates a clock signal. Now our binary counter doesn't produce octaves in this case. No, it counts from 0 to 255 in binary. It's the exact same circuit, yet the function we give the circuit actually defines where it's analog or digital. So, and this is exactly what was my problem with that whole discussion with that, that little synthesizer drone box. It wasn't a digital synth, because it was not designed to function in binary, you could say. It wasn't designed to work with binary data. It wasn't designed to compute the oscillators or sound waves using binary, using digital logic. Instead, the synthesizer used digital chips, digital logic, in a way that it generated all sorts of analog, square wave and pulse sounds and all sorts of noise. But it is analog in the way it works. It is analog in its functionality. It is an analog synthesizer. Now, most people say, well, a digital signal is only is a signal that's between low and high. It only has 2 states. And an analog signal has an infinite amount of states, infinite amount of voltages. Now, of course, this is true, but it kind of illustrates a train of thought which is not entirely correct, in my opinion, as I illustrated with these concepts. So yeah, that's my 2 cents on the subject. Let me know what you think. Have a discussion in the comment section. I'm happy to know your opinion, your thoughts about this. And well, if you like this video, comment and like and subscribe and all that fancy stuff. And I'll see you guys next video. Bye bye.